Stephanie Earp from Space Intelligence, on country scale Landcover and carbon mapping.
Great, thank you. Before we begin, I am losing my voice, so let's see how this goes. I have manically added a few more bits of text to the slide just in case you can't hear me. I did that over lunchtime, and I got my preferred LLM to give me some key takeaway slides that I've punctuated throughout the talk, so that if you can't hear what I'm saying, there's like at least 3 slides, and that's all you need to know. You don't need to know anything else I'm saying. So yeah, I'm from Space Intelligence. We're a company based in Edinburgh that produces Landcover maps and carbon maps. I'll talk a bit about what we are and what we do. I'm here with my colleague Christian, who's one of our senior research engineers in the company. And I'm going to do a very high-level talk today about the problems and challenges in our space, what we do in terms of Landcover and carbon, what I believe is coming up next and what I believe is important coming up next. And this is really my ask to the community of these are the things that will help us, that will help influence the bigger picture in industry in terms of the policy and everything else. So yeah, Space Intelligence, as I said, we're based in Edinburgh. We really focus on high accuracy nature data. So our mission as a company is to stop deforestation and enable afforestation and reforestation projects. So our key areas we work in are the tropics, tropical forests, and looking at that, understanding the degradation or the deforestation, and enabling, giving data to enable people to start protecting these forests. And we do this at scale. So in the past 18 months or so, I think since about June last year, we've mapped all of these countries in green, and the one in yellow have now been done as well. So it's over 50 countries and billions of hectares, and we do this at 10 meter resolution pixels. So we've terapixels of data we've mapped and put through our machine learning models, and got out Landcover classifications for all these areas. And my main takeaway from this slide is we are very anti-Mercator projection. We work mainly in the tropics, so we don't show that because then it looks like we've hardly done any work. There's one for the map nerds among you. But we as a company are really focused on the science-backed nature of what we do. The company was founded by 2 professors from the University of Edinburgh, brought their research into the company as a spin-out and built along that. One thing I am going to highlight we're particularly proud of is our African squirrel that we have appeared to have mapped here within our countries. Our mapping process, how do we do this? Essentially, we take a lot of data. So we use all kind of the classic open source satellite data, optical data, radar data. A lot of you in this room all know all about these types of things, and LiDAR data. These are all the ones that are available open source from NASA, from ESA, from JAXA, the Japanese Space Agency. And we use machine learning models to create these data sets at scale. But what is really key for us is this human in the loop part that we do. And we have a team of ecologists, a really core part of our company, who really put in that local knowledge, that understanding of what's going on the ground and how can we make our models better. And what I'll show you throughout this talk is why that is so important. So yeah, that's my Space Intelligence kind of advert for anyone who wants to know about us. I don't really need to explain this slide to you. We've already touched on a bit on climate change in the first couple of talks in this session, but this is mainly to emphasize the part that when we think and when we talk about climate change, a lot of that focus is on fossil fuels and stopping fossil fuels. And that's what we need to do to solve the climate crisis that we're in. And as a bit, and unrelated to my presentation aside, it is quite nice that here we're seeing now that the fossil fuel use is getting flat and not increasing. So there's a positive. But what we don't talk about as much is this part, the net land use change, and this is the change from deforestation. And it's a small part, but it's still a really significant part to this process, and this is what we can do as a company, what we do to help also reduce the effects of climate change here. And the way this is done is through the carbon credits. So as you all know, and we've all talked about that, everyone's committed to being net zero by 2050, and a lot of people need to do it sooner, and all these companies have all these big kind of targets of where they'll be, and Apple is a company that we have worked with on their nature-based solutions fund. I skipped over that part of the slide, but it's like £400 billion. So there's a lot of money we're talking about that they're putting in to try and get to net zero by 2030. A lot of that can be done by reduction, but not all of it. Apple make phones. There's a lot that goes into phones that you can't do carbon neutrally, so they have to offset it somehow. And that's where we come in as a company, and we provide that data so that they can find the best carbon projects to invest in, be that stopping deforestation, protecting areas of tropical forest, or funding underdeveloped countries to enable it to do them themselves. So I'm bringing this up because this is the kind of the background and the landscape to what we're doing and what we work on. But for me, key to a lot of this is the certainty aspect. We focus on high accuracy products, we focus on getting the right answer. And that's really important, because if we don't, people lose trust. There's always been a lot of controversy around carbon credits. And if we're not understanding the science and everything behind what we do, we're not going to be able to get that trust out to the market that what we're giving is actually accurate results. So I said there's billions of pounds of climate finance that is coming. You can boil it very simply down into two questions, and that is, where are the forests and how much carbon is in them? And if we can't do that accurately enough at all the scales we need to do it at, then no one's going to trust us, and no one's going to, protect forests and stop deforestation, because they think we're all lying, essentially. This here kind of exemplifies quite well. This is an open source product from ESA, I think, that's biomass product. That's basically, you can see here where the forests kind of are across the world, but what are the most the highest biomass forests? So these are the forests with the densest amount of biomass per hectare is how we normally do it. And you can see it's the tropics. There's Southeast Asia, there's Central Africa, and then there's the Amazon. And it's these areas where we as a company tend to generally focus. So the majority of approaches that are happening now, and that I've done in the past, and what people are building for the future, are very much deterministic algorithms. This is essentially particularly the where are the forests is a classification problem. And people tend to do this on the assumption that there is a correct answer, and on the face of it, kind of sounds like there would be, because is that a forest or not a forest? You think you could tell. But there's a lot of complexities within this. For example, does anyone, and I'm going to throw this out, people think, how would you define a forest? Does anyone want to, the people that kind of know the answer to this, they shout out, but what would you think a forest was?
More than 10 individuals with diameter at breast height of above 20 centimeters per whatever unit of area, hectare.
Yeah, no, it's exactly that. You're getting all that. Those are all the things that people think of. So it's how many trees, what area, what height, that type of thing. So you think it'd be easy to define, but in the case of some countries, it's 10% canopy cover. So if you take a hectare, you need 10% of tree canopy in that hectare to be classed as a forest. In other cases, it's 40. And in some cases, the tree height is kind of 3 meters. In other cases, it's 5 meters, and it varies by country. Mm-hmm. So to answer the question of what is a forest, you go, well, where do I live? Essentially. So there isn't ever a single correct answer, which is why my thesis to you guys is it's not about finding the answer. It's about everything that goes around it. Is what is the certainty in that answer? How do we quantify what that looks like? And this is my first takeaway for those that can't understand me. We're very good already at knowing what the answer is. And you'll see in the next slide. But it's about knowing how sure we are, or being able to describe why we think it's that answer. And as an example to this, I love this image because it just tells you everything about the landscape of open data Landcover products. Here we've got 6 different Landcover products, and as you can see, they've been, so this is the Landcover at the top. And then here on the next row, you've got the data that went into making it. So you've got some optical data and some radar data. And some use just optical, some use optical and radar. And then you've got all the classifications that they use. And they're all different. So we have these global products, but each data set has its own strength and its own focus. And you can never get one that will answer all of your questions. There's very much a trade-off. And at a global level, these are all great in their own aspect. But if we start looking a bit closer, so we can see here on this Sentinel-2 image, that there is a bridge. And you can just about, it's here, it's in this one. It's not really in this one, it's kind of trying. It's not in this one at all. It's not in that one there, it's much coarser model. And that's a bridge. That's a bridge over the sea. That's really easy. That's not, bridges are bridges. It's not like forests and definitions. But then you can see there's other aspects here. So this here I looked at, this is an airport. And where's the vineyards? This one, they have vineyards as one of their classifications. And up here, you appear to have the airport, which is the bare land, which, according to this, is cultivated, surrounded by vineyards. Now, I don't know about you, but I don't think I'd want wine from there. But everywhere in this map, we have slightly different classifications. Here it's grassland. Here it's cropland. Here it's vineyards. Here it's artificial mining and dumping sites, and over here it's built with some grass. So that's just six products that all tell you different things, and at a local level is very hard. And this is a really kind of important and nuanced thing that we deal with in space intelligence is, yeah, these global data sets are great, but people need local answers, and the key to understanding what you're looking at is like, what scale are you thinking of? So for us, we make a lot of products for EEDR. So EEDR is this EU regulation that says no crops such as coffee or cocoa can be imported into the EU if they've caused deforestation since 2020. And originally when people started doing it, they thought, great, we've got Global Forest Watch, we've got Hansen, we've got JRC Global Forest Cover. These are all global forest data sets. We can just use those. They all look very different. And these are all supposedly telling us what a forest and what a not forest. Now, what they don't tell you is these aren't forests, these are tree cover. Subtly different. But if you were to try and take this at a local level and tell farmers, if your farm is in that green belt, you're not allowed to sell your products to the EU. There's a lot of local farmers in various countries then going out of business because we are not using and understanding our data in the correct way. So this is the space intelligence map down here that we made. And we did this on a more local level, and we used information about farm data to really understand what was going on. And I'm now going to show you why it's hard. No, I'm not. I'm going to do that in a minute. What I am now going to talk about is the next part, which is foundation models. So we have all these open data sets that people have been using, and they make them standard convolutional neural networks, classify forest, non-forest, do it over a global scale, produce something like this. Great. And now, in the last few years, foundation models started coming in. So Global Forest Watch, which if I go back, is this product here. Started 14 years ago. And it took 10 years, tens of millions of dollars, and hundreds of data scientists to build this up. And back then, this was such an achievement. We've come a long way since then. 8 years later, reduced, by an order of magnitude, the amount of time and effort and people it took to make another global product. Again, another order of magnitude for another global product, illegal mining sites. And what the promise now, this is from a company called Clay that want to be the ChatGPT of the Earth observation world. They're saying you can do it in an hour, no cost, no expertise. Now in reality, that's marketing hype. And it's not true, and they know it. It's a very intelligent man that runs Clay. But this is the kind of the sale. This is the marketing. This is where people think things are going to go and how you can get the best answers. Now I'm going to show you the reality, and this is why when we're doing what we do, it's so hard. And before I do, I'm going to give a shout out to Lennart, who I believe is online. He was an intern with us at Space Intelligence at the beginning of this year, and we tasked him with differentiating between cocoa trees and forest in areas where it's very mixed. We gave him some data, we gave him some polygons of areas and kind of said, "Here's what you can do." And he very quickly joined one of our chat groups. So he said, "Hi everyone. Would you label this pixel on the polygon as cocoa? Seems a bit of mixed vegetation, could be scrubs, looks like cocoa, not really sure, does kind of look. There could be some shrub. What would you do?" So this here, he's taken this square here and he's gone in. And he put this out to a group of our data scientists and ecologists who do this for a living. And what he got back was, no idea. Looks like a mix of different tree crops. Let's just call it dense forest. We've seen, it's tricky. Definitely a lot of planting. Must call it plantation crops, but not cocoa. I don't even want to label that pixel. So these are our experts, right? This is what we're dealing in. Every day people going, well, what even is this? Which leads to my next big thing. So our data was nuanced, right? There's not, as you can see from that picture, you could be forest, could be cocoa, unless you go on the ground and you walk around every aspect of the earth, you're not going to know. And this is why it's important, because it's no longer about what is that pixel. It's about what can that pixel tell us, how are we getting to the idea of that pixel, and the data is nuanced. Because this is what's coming, this is what's next. These people, Global Nature Watch, they're the same people that did Global Forest Watch I showed you before. And it's all LLMs, right? So we've got all this data, we've got all this cool stuff, and now we want to bring the LLMs into that, and we want to take this data and then output something that's text that can tell people stories. But the issue here, and the issue you can see, there is at the bottom this very small thing that says AI can make mistakes. But otherwise, it's presenting you this lovely graph and this lovely analysis, and it's all very certain. And they do a very good job of, you know, plotting out the data, telling you where it came from. There is evidence of what data it's using, but someone could very easily come to this and think it's truth. And that's not the fun part. The fun part is us being able to say, well, this is the changes in grassland because probabilistically we've looked at these models and they tell us this. They tell us that what is going on behind the scenes in the data we've made is giving us these insights. So I'm gonna, that's basically the summary. We don't want to give the answers. We want to say why. We want to give the confidence. We want to tell people how much we know what's going on. Because the reality is, it's not as black as white as that. And I've been way over keen on how much I can get through on this talk, so I will go on to bypass now. Basically, once we've worked out where the forests are, we need to know how much carbon's in those forests. And we can measure carbon stocks. The true and only method of doing it is chopping down a tree. You can't do everywhere to find out the carbon. Calorie is the whole point of saving the trees. But there are mathematical equations we can use this, and essentially you can estimate it. It's a function of the height of the tree, the width of the tree, and the density of the wood, so the type of tree that you're using. And as you can see from the image I showed you before, that's actually quite complex. There's never just one tree in a nice 10-metre square box for you to measure. It's a bit more nuanced than that. And also, we can't measure all the trees. We have to do this in a remote sensing way. The way we do that is LiDAR. So there are satellites, the JEDI satellite that uses LiDAR data, and it can shine, it looks down on Earth, and it emits the LiDAR signals, and you can get back these lovely graphs, which can give you the kind of top tree height. So this would be related to this up here, and this ground return would be what's down here, and then you can, from this, kind of calculate the tree height. It's a lot more complex than that, obviously. The problem with this is it's a satellite, so it goes around the Earth in very specific tracks, and the data we get from it is very sparse, very linear, sampling bias, all that fun. But we can take that, and we take that JEDI data, and we can use it, and it's essentially a machine learning problem of extrapolation. We have the data, what we have. We can then take that height, and we can use equations to turn it into biomass. This is my only equation of the talk. You can make this as simple as complex as you like, but essentially, you're trying to find something that fits, that describes the trees in the area you're working. And there's a lot of uncertainty in this. The uncertainty in working out these carbon maps is quite complex. You have your height modelling, which is your errors in your height measurements, or the location of the satellite, and your sampling bias, and all of that. And then on top of that, you have your errors in your allometry modelling. So just the fact you can only measure 15 trees, and they're probably all going to be in a really close area and not representative of the larger area. The equations you use are going to be approximate. It's really hard to actually get a proper geolocation in the field in the middle of the Amazon in Peru, so you're never going to know exactly where those trees are. All of this comes together, and it's very much kind of additive. So the errors you get in the height modelling, when you take that over to the allometry modelling, they're all linked, they're all related, and you have to deal with this. And the way we do that is really important, because it's about going back to the very beginning of my talk, this is about credibility. People need to know how much carbon's there, so they know how many carbon credits to sell, so you don't oversell them and then people like The Guardian shout at you. So this is really important, and lots of people try to do frameworks to make sure people can't game the system, but also give the flexibility that we can innovate as scientists. Problem is, you end up with stuff like this. And this is basically add up all your potential carbon units. That's pretty ugly. And it only gets worse. And I have not got through a single one of these standards without my eyes bleeding. But when we get to uncertainty, we're getting these massive equations. This equation here is basically saying, this is the sum of the squares of everything. That's all it is. That's a full page of the standards. So this is what we kind of deal with. This is what we have to fit into. Yeah, also trying to be scientifically accurate. So in reality, how we do this is we train height models, and we have our very kind of crude. I'd say crude. It is not. This is prime for probabilistic AI. Is we will take our Jedi data and we will train a height model, and it will look something like this. And then to capture all the errors, we essentially create ensembles. We can do this in a variety of ways. We add noise to our data to try and take into account the errors in the sensors or the geolocations and all that. And from that, we can take the means of our AIs. These maps all look very similar. The way we do it is we look at our means, so we can get a distribution of probable heights in our models to understand what's going on. But the models are very sensitive to input data. And the most interesting thing here is train is cheap. We only have a set amount of data. The Jedi lines are very thin. So over a big area, there's not that much to train on. The expensive part is the inference. When we're doing this over ensemble modeling, we have to do this inference 40 times, 80 times, 100 times over large areas. And I'll give you an example here. The Amazon is 105 billion pixels if we wanted to do this over the Amazon. So the issue we have isn't the training, isn't large models. It's how do we get this out in a sensible way over a really large area. And then the same with allometry. This is very much ecology, so I won't go into this too much. But we take our height models and we take our suite of height models and we can apply equations in the same bootstrapping way. For these points here, which are field plots, we have errors, we know things, we estimate things, more ensembles, more modelling, until we eventually get a distribution of the mean of biomass in that area. And we're fairly happy with that. The problem comes with change. And change is important because that's what people want to know. They want to know, how has the carbon changed in my area over the past 5 years, 10 years? And it's really hard. Because we work over such large scales and there's such large errors in all of our pixel uncertainties that we do, we have to rely just on error cancellation over large scales. But ultimately we are able to produce kind of distributions of possible change. So here for this example I showed you, change over 13 years this was, you can see the areas of deforestation in red and the areas of growth. But this is kind of the lower end, the median, and the upper end of what would happen. And the mean values you can represent by this distribution. And this in itself is a big shift. Most people just have 3 numbers. I'm running out of time. So one thing, I'm just going to do this, I'm out of time. So one thing I will say is, the probabilistic element currently is kind of being ignored because people don't know what to do. AI got mentioned in the talk before lunch about AI slop. Foundation models and AI hype are a massive thing at the moment in this space, particularly in Landcover mapping. And this current trend is just promising this one-shot answer. And my ask for you and for this community is, let's not think about it like that. And let's start thinking about it in terms of not what is the answer, but why is that the answer? That's my final take-home point for anyone who can't hit me.